Hello, welcome. We are going to continue our study of hypothesis tests with section 7.3. And we're looking now, the case, this is similar to 7.2, except for now, sigma is unknown. So we're still testing for the mean, but now we're assuming that sigma is unknown. This is actually the most realistic case between section 7.2 and 7.3 because typically you don't know your population standard deviation. You only have your sample standard deviation as a reference point. Okay, and similar to chapter 6 when we're working with confidence intervals, here we will have two tests. So last section in 7.2, when sigma was known, we used a z-test. Now in 7.3, sigma is unknown, we're using a t-test. And of course the z here is a reminder that the probabilities are based on the z distribution, and this t is an indication that our probabilities that we're computing are going to be based on a t distribution, right? And the reason why this is similar to the confidence intervals is because when sigma was known, we used z interval, right? Do you remember? And then with sigma unknown, we used t interval. Okay? So we'll have some similarities that we're going to be able to kind of lean on in terms of the parallels between the two cases. Okay, so we've got three objectives for this section. The first one is to find critical values in a t distribution. That is going to involve our inverse t function on the calculator. The second is to use the t-test to test a mean, mu when sigma is not known. And the third is using technology to find the p-values and use them with a t-test to test a mean, mu. Okay, so I've got two comments that I'd like to make. Number one, when we are finding critical values, you'll notice this is kind of a general comment, chapter 6 versus chapter 7. When you are finding critical values for a confidence interval, that is different than critical values for a hypothesis test. Sometimes they're the same, but sometimes they're totally different. Because, so here's the comment. The first comment is that critical values for a confidence interval, for confidence intervals, versus critical values for hypothesis testing. Now, critical values for confidence intervals, for example, a critical value for a confidence interval is always positive. Whereas critical values for hypothesis testing could be positive, could be negative. Right? You only have one critical value for a confidence interval, whereas for critical values for hypothesis testing, you could have one or two. Okay, so keep in mind how we find our critical values is a little different. So here, when we're doing a critical value for hypothesis testing, the way we find the critical value changes based on if we have a left-tailed, a right-tailed, or a two-tailed test, right? Because based on your alternate hypothesis, I forget how it's pronounced, which word it is, but based on HA, either you're doing a left-tailed, right-tailed, or two-tailed. Okay, so for instance, in this first case here, right, so in this case here, you only have one critical value, and it's the value that's right there. And over here, you only have one critical value. It's the value that is right there. But if you're doing a two-tailed, then you've got two critical values, right? Now, for critical values for a confidence interval, there's only one, and it's always positive. And the way we find the critical value is, well, that's in an earlier video, so I won't go over it now. But so just keep in mind and be aware, for instance, if you're using websites online or online calculators or anything like that, keep in mind that if you say critical value, you need to be sure that you know what the critical value is used for. Is it for a hypothesis test or is it for a confidence interval? Okay. All right. Now I've made these. This little chart here, and this is I think a helpful guideline because there are actually two ways to perform hypothesis tests. There's the way using p-values. This is the way that your calculator does it, right? So when we're using our calculator is using p-values. The output is a p-value, which stands for probability value, right? That is a newer way to conduct a hypothesis test. The older way, the traditional method, is using critical values, okay? And so the textbook presents, and I also present both methods so that you're aware, because you might be reading, an article or, looking up something in a journal, and they might use the language of critical values for their hypothesis testing. And you want to be familiar with it. You want to say at least, oh yeah, I remember something about a critical value method, kind of be able to refresh your memory. In general, the new way to do it is with p-values. So on the MyLab, right, the MyStatLab homework, there will be problems that require you to do both methods, right? So there'll be some problems about using the critical value method. There will be some problems about using the p-value method, right? On the written homework that you submit, it is your decision, it's your choice how you want to conduct the hypothesis test. If you want to use the p-value method, you can do that. If you want to use the critical value method, you can do that. Whichever, feels comfortable for you, whichever one you prefer. And the same thing goes for on the exam. So as I said in class, on the exam, we're going to have just a list of word problems, essentially, where it says conduct a hypothesis test, create a confidence interval, right? And you'll choose, maybe you'll choose 4 or 5 of them or however many you want, or not however many you want, but you'll have several and you'll get to choose from, the problems on the sheet, and then you'll be required to fill out a form, right? So you'll figure out, now what kind of form do I need? Am I doing a 1 sample hypothesis test? Am I doing a 2 sample? Is it for the mean? Is it for the, right, standard deviation? Is it for the proportion? So you'll figure all that out, and then you'll fill out this form here, and this kind of walks you through the steps of performing the test. And so this is why you're having this as part of your written homework, is to prepare you and get you ready for the in-class exam, right? So what I want to do is I want to talk about the differences between the two. Now we've already seen both of these guidelines, both of these methods. The first step is always the same. It doesn't matter. The first step is always the same. The first step is essentially to verify that you can perform the test, right? So that's going to be the same, and it's regardless of whether you're doing a t-test or a z-test or whatever test, you have to verify that you meet the requirements, right? And then the second step is also going to be the same. Determine your null and alternative hypotheses, okay? And we've got some steps to how to do that. And then the third step which is a really quick step because this is typically written in the problem, or it's up to you to figure, you can set your own alpha, right? Determine alpha. So you can set your own alpha unless, say, if you're working on a problem and it says use alpha equals, 5%, well, then that's the alpha you should use. But that's relatively quick. Here's where we get into the difference. So for the critical value method, you're finding rejection regions. And so your steps 4, 5, and 6 are going to be slightly different, are going to be drastically different actually, than if you are doing the p-value, because with the p-value, you'll just use the t-test on your TI 84. With the critical value method, right, and doing the rejection regions, you'll need to determine your standardized test statistic. You'll need to determine your critical value in your rejection regions, right? And now, which test you use is going to impact how you make a decision, but for both steps, for both methods, making a decision and interpreting your decision are the last two, right? Are the last two steps in the methods. Okay. So the change, or where things differ, is these little steps here, 4 and 5, 4, 5, and 6, and then 4, 5, and 6 over here. That's where you get the distinction. Okay. So now, and just to have it as a reference, and I'm gonna put it here. It might be something worth taking a screenshot. This is really handy to have. First thing is making a decision. How do you make a decision? Well, the first thing to note is the decision is always one of two options. You're either going to decide to reject H naught or fail to reject H naught. Accept H naught is not a decision, right? That is not an option. Your decision is never going to be I accept H naught. Your decision is never going to be I accept HA. Those cannot be the outcome. Neither of those can be the outcome. Outcome of performing a hypothesis test is either reject H naught or fail to reject H naught. And now how you determine whether you're going to reject H naught or fail to reject is based on, it differs based on the method that you're using. So if you're using the p-value method, you just ask yourself one simple question. Is the p-value, which you'll get from your calculator, because you'll get this will be on, from your calculator, you'll get a p-value from the calculator, is that less than or equal to alpha? If it is, then you reject H naught. If it's not, you fail to reject H naught. If you're using the critical value method, then you ask yourself one question. Is the standardized test statistic in the rejection region? If it's in the rejection region, then reject, right? So that, it's in some ways this is simpler to remember, because if it's in the rejection region, reject H naught. If it's not in the rejection region, then fail to reject H naught. Okay? And now the last step again is interpreting your decision. And now here's how we read this chart, right? So when you're interpreting your decision, it's based on two factors. Is your claim H naught or HA? Is your claim H naught or HA? And the second question is based on is, did you reject H naught or fail to reject H naught? And then based on that, so for example, if your claim is HA and you rejected H naught, then you look in this column here, my claim is HA and I rejected H naught, so then you go over here and over here, and so this is your conclusion, right? This is how you interpret your decision. There's enough evidence to support the claim. Okay, so you kind of read this chart here, and this tells you how to interpret your decision. And what decision is that? Your decision of rejecting H0 or failing to reject H0. Okay. All right. So what we're going to do is, in this video, what we're going to do is we're essentially going to, we've got three examples. Example 1, example 2, and example 3. Okay, so we've got 3 hypothesis tests that we're going to perform. And I'm going to perform them with, I'm going to do the one example using the critical value method. I'm going to do another example using the p-value method. And then for the third example, I'll figure out whichever one I feel like doing. And then I will fill out this little, this chart here, this table. So you have an example of, hey, what do you need to do? You have an example of how to fill out this form while you are performing the hypothesis test. Okay, so that's kind of idea. Now the first example that we do, we're going to use critical values. So we're going to do the critical value method. And so in order to do the critical value method, we already know how to verify that you can perform the t-test, right? We know how to determine your null and alternative hypotheses, because we got practice with that in section 7.1 and section 7.2. We know how to determine alpha, right? We'll just read the word problem. However, here's what we need to do. We need to work on, what are my critical values, right? So how do we find a critical value? Because remember, in this section, sigma is unknown, so we're finding critical values in a t distribution. Okay, so in order to find the critical values, first thing you got to do is you've got to know alpha. So you've got to know your significance level alpha, and then you also need to know your degrees of freedom. And now, of course, for us, instead of using the table in table 5 in Appendix B, that's not going to be helpful. That's not going to be helpful, right? What we're going to do is we're actually going to use our calculator. We're going to use not inverse norm, but we're going to use inverse t. So let's go ahead and so in fact, we don't need all of this column with a negative sign and a positive sign and and multiply it by 2. We don't need all of that. Okay, here we go. Find the critical value t0 for a left-tailed test given that alpha equals 0.05 and n equals 21. Okay. So, once we know that it is a left-tailed test, that tells us that we can draw a sketch, and it's going to be something like this. Okay. And what we want is this value right here. This will be our critical value. Remember, when we want to know a value and we have an area, we use inverse t. Okay, we're given that alpha is equal to 0.05. So what that means is, that we've got a 5% maximum tolerance for making a type 1 error. That means that this area is going to be 0.05, right? This area is going to be 5% of the entire area under the distribution. Now that we know that n is equal to 21, that tells us that our degrees of freedom are n minus 1, so it'll be 21 minus 1. We'll have 20 degrees of freedom. And we're going to need that because we're going to type in inverse t. So find inverse t on your calculator. How do we do that? Go to second vars. So if you click second and then vars to get to your distributions, plus vars, and then scroll down, and for me it's number 4, inverse t. Okay, so now click inverse t, hit enter, and now where it says area, we need the cumulative area. The cumulative area is 0.05. For the degrees of freedom, there are 20 degrees of freedom. So let's see here, 0.05 for area, 20 degrees of freedom. We hit paste, and I got negative 1.7247. And so that is my TC. So let me in fact write this a little larger here. So TC equals negative 1.7247. And now once I have my critical value, then I know my rejection region is, let's blow this up here. My rejection region is anything, so I'm trying to make this a little clearer. Okay, so this area in here is 0.05, right? My rejection region is anything less than, any value that is less than my critical value, negative 1.7247. Okay, and we can look here and notice that we have here here's a picture. Now these one thing that I don't like about these pre-made slides is that they're kind of misleading because the area is in blue. Okay, so the area is in blue. The rejection region is, this is in red. So the rejection region is in red. And then your critical value TC is right here. And it's fine. They rounded it. We didn't round because this is using a table or a chart or something, so they're limited in terms of how accurate they can be. We have our calculator, so our calculator can give us as much accuracy. We can be as accurate as we feel like. Well, not really. We can be as accurate as with the calculator, the output of the calculator. But that's good enough. Okay. So don't worry if there is a discrepancy between these two. The calculator gives you something that's more accurate. When you are filling out your exams, when you're doing your written assignments, I'm not just looking for a final answer. I'm looking at the method that you used, and I'm looking at you showing your work. So I'll be able to tell if you know what's going on, if you know what you're doing, based on looking at all the work that you do. Okay. Now, what about here? Let's find the critical values for a two-tailed test. Okay, so we've got a two-tailed test, and we're given that alpha is equal to 10% and n equals 26. Okay, so I sketch, and I'm doing a two-tailed test. So I know that I've got some to the left and some to the right. I've got a left tail and a right tail. Now, if alpha is equal to 0.10, that's the same thing as saying alpha is 10%, right? So that means that the area in each tail needs to be 5%. Why? Because I've got 10% and I need to split it among two tails. Each tail should have 5%. Okay, so now if this area is 0.05 and this area is 0.05, now this is going to be minus TC and this is going to be my critical value TC. Okay, so how do I put this in the calculators? For the first one, for minus TC, I'm going to use inverse T. For area, I'm going to put 0.05. For degrees of freedom, let's see here, n is equal to 26, so my degrees of freedom should be what? 25. You got it. Okay, so now what do we have here? Let's see here. Inverse norm. So 0.05 and then 25, and I get negative 1.7081400693. Hey, isn't that exactly what we had before? It almost is. The reason why it's not exactly the same is because my degrees of freedom are different, right? So in this first example, I've got 20 degrees of freedom, whereas in the second example, I've got 25 degrees of freedom, okay? So I've got 1 TC. Now notice this value here is the same as this value on the left, right? So one of my critical values is negative 1.708. Now let's figure out, let's investigate how to find the other critical value. Because remember, if you have a two-tailed test, then you will have two critical values. Okay, so to find that TC, I need to know, here's what I need to know. Let me put it back up here. I still need to know the cumulative area. So I need to know the cumulative area. The cumulative area is going to be the area to the right. So now what is the area to the right of this value? It's going to be everything back here. Okay. So the area to the right is in purple. The area to the left is in blue. Okay. Now, what is the area to the right? Area to the right is going to be 95%. Because remember, all of the area is going to be 100%. So if the area to the left is 5%, then the area to the right has to be 95%. So TC is going to be inverse T. And my cumulative area is going to be 95%, 0.95. And my degrees of freedom are going to stay the same. They're going to be 25. Okay. And now when I put that in, let's see here, I get 1.7081400693. Okay. And that's good. We're happy. That makes sense. Because T distributions are symmetric, I actually didn't really need to compute TC using inverse T, because once I know one of them, then I know the other one is just going to be the absolute value of it. Okay, so we've gotten practice finding our critical values. Okay, we know how to do that. And here we have this is the general information telling us what is the test statistic. The test statistic is very similar to a point estimate, right? The test statistic is what is the statistic that we are going to use for our test. Once we have the test statistic, which is going to be the sample mean, once we have that, we need to standardize it. And so in order to standardize it, this is our formula, right? So we've got X bar. So in other words, we've got our test statistic minus the proposed mean, right? So remember, when you set up your null and alternative hypotheses, you'll have an assumption, right, that you're working off of, mu equals mu naught, or mu equals k. We want to know what is that proposed mean. And then we're going to divide by the sample standard error. Okay, that gives you, that's what we're doing when we are standardizing our test statistic. And the last little point here is we'll need to know our degrees of freedom. We already know that, n minus 1. Okay, now this is a synopsis of kind of what I wrote before. Step 1 is to verify that you have what you're supposed to, that you meet the requirements that you need to meet to perform the t-test. Step 2 is to get that null and alternative hypothesis. Step 3 is to identify alpha. And then step 4, right, all of these, I kind of combined them into 4 and 5 before. And then the last two, make a decision and then interpret the decision in the context of the original claim. All right, so we're ready. Let's do this example here. A used car dealer says that the mean price of a 2-year-old sedan is at least $20,500. You suspect this claim is incorrect and find that a random sample of 14 similar vehicles has a mean price of $19,850 and a standard deviation of $1,084. Is there enough evidence to reject the dealer's claim at alpha equals 0.05? Assume the population is normally distributed. Okay. So now looking here, it appears that we need to use a t-test, because what I'm going to do is I'm going to highlight all of the information that we've been given. So a used car dealer says that the mean price of a 2-year-old sedan is at least $20,500. You suspect this claim is incorrect. Notice that it's telling you that, hey, what you just read is the claim. Okay, you suspect this claim is incorrect and find that a random sample, okay, so that's important, random sample, 14 similar vehicles, has a mean price of $19,850. And that random sample has a standard deviation of 1084. Is there enough evidence to reject the dealer's claim at alpha equals 5%? Assume that the population is normally distributed. Okay. So what we're given here, for instance, is we're given that n equals 14, right? Because we have a random sample of 14 similar vehicles. And the random sample has a mean price of $19,850. So that means that X bar is $19,850. And a standard deviation of 1084. So that random sample has a mean price of $19,850 and it has a standard deviation of 1084. So that means S is equal to 1084. We're also told that alpha is equal to 0.05. Notice that we do not have sigma. Sigma is unknown. There's nothing about a population standard deviation. Sigma is unknown. That tells us we need to perform a t-test. If they told us sigma, then we could perform a z-test. They didn't tell us sigma. We don't know sigma. We need to perform a t-test. Okay, so let's go ahead and check off this checklist here. So verify that you can perform the t-test. Verify that sigma is unknown. Okay, we just did that. And then we are only given S. I think the S we're given is S equals 1084. Okay. Verify that the sample is random. We can verify that because that's stated in the problem right here, right? Random sample is stated in problem. Verify stated in the problem. Verify that population is normally distributed, or n is greater than or equal to 30. Let's see here. Assume the population is normally distributed. So check mark, maybe say stated in the problem. All right, number 2, determine your H0 and HA. We need to write down the claim using everyday English words. The claim is that the mean price of a 2-year-old sedan is at least $20,500. So the mean price, average price of sedan is $20,500. Now, how do we translate that into math? Let me actually move this down a little bit. How do we translate this into math? Average price of sedan, that's the same as mu. Right. Average price. If you say, what is the average price of a 2-year-old sedan? You're asking me for the population mean. Is. Do you remember is? What does is translate to? Equal sign. And then, of course, the 2,500. You see how that works? So if you have done if you've done a good and thorough job on this first part, right? If you've done a good job here writing down the claim, you should be able to translate it without having to look back at the word problem. Just say, oh, this is my population mean. Is equal sign, and then 20,500. That's just 20,500. Okay. Now, we've translated into math. We wrote down the claim. We need to write the complement. What is the complement? Complement is going to be mu not equal to 2,500. Let me go back. Because it says that the mean price of a 2-year-old sedan is at least. So I forgot this at least. And that makes a difference. So let me go back and modify this. So the average price of a sedan is, let me modify that, at least $20,500. Now, how do we translate that? Average price of sedan, that's still going to be mu, is at least, let's see, now this is a little different, is at least, how do we translate that? Mu greater than or equal to, and then the 2,500. Write the complement. What is the complement of mu is greater than or equal to 20,500? Mu is less than 20,500. Figure out which one is H naught and which one is HA. H naught has to be the top one because of this greater than or equal to. So H naught is mu greater than or equal to 2,500. And then HA, mu less than 2,500. Now, which one is our claim? Our claim, remember, this is our claim, this was our claim. And then we translated it into math, so this is our claim. And then this is the complement of our claim. Complement of claim. So I'm just going to indicate down here that this first statement is our claim. It might look funny. It might look like, hey, we've got too much stuff going on. But this is actually, this is the setup. So we need to write, let me in fact show you how we're doing it one more time. We need to write H naught and then a colon. So you're letting the reader know what follows this colon is going to be my null hypothesis. And then HA colon. What follows the colon is going to be my alternative hypothesis. Please remember that the claim does not have to be the null hypothesis. The claim does not have to be the alternative hypothesis. You don't know which one is the claim. It depends on the wording of the problem. Okay? So in this case, it just happens that my null hypothesis is this statement right here. So I'm going to put mu greater than or equal to 2,500, and that just so happens to be my claim. Whatever's left over is my alternative. So mu less than 2,500 is my alternative. The reason why I'm indicating that it's a claim right here is because I know when I get down to this last, oh boy, I didn't mean to do that. When I get down to this last one here, which is interpret your decision, I'm going to need to know if the claim, right, so let's look back. Remember, when you're interpreting, I need to know, is the claim H naught or is the claim HA in order to interpret my decision. So in my mind, I'm going to remember, the claim is H naught. So this is the column. I'm looking at that first column in terms of interpretations. Okay. So here we are. So we've got our null and alternative hypothesis. Good. Determine alpha. Easy. We already said alpha is 0.05, right? Because it is written in the problem. Alpha is 0.05. Now we need to determine your critical values and rejection region. So in order to determine my critical value and my rejection region, I need to see what type of test am I performing? Left-tailed, right-tailed, two-tailed, right? Use HA to figure out if you are performing a left-tailed, right-tailed, or two-tailed hypothesis test. So based on HA, since our HA is mu less than 2500, that's our HA. So we are performing a left-tailed test. How do I know? Because I've got mu less than 2500. So whenever it's mu less than, I'm doing a left-tailed. Okay, so I kind of sketch a picture here. Okay, I'm going to be doing a left-tailed test. So it's going to look something like that. This is a t distribution, right, because sigma is unknown. I'm doing a left-tailed test. And I need for this area to be equal to 0.05. So TC is going to be inverse T. My cumulative area is 0.05. My degrees of freedom are, how many degrees of freedom do I have? I've got, it needs to be n minus 1. N is, do you remember that? So n is my degrees of freedom, 13. And yet, I should get rounded off negative 1.7 and 1, okay? Well, I can be more precise than 0.5 degrees of 13. I negative 1.7, just to make you can make sure you're doing it correct. Negative 1.7 and 0.93376, and then we're going to round that off to 0.71. Okay. So rejection region could be anything. That's too wide. Okay. My rejection region is going to be anything that is less than negative 1.7. Let me get that down. So rejection region, any number less than negative 1.7709. Okay. The next step is to determine your standardized test statistic. Now, to determine my standardized test statistic, I need to know what is my test statistic. So, did you write down the formula for standardized test statistic? It is written right here. So remember, this is our formula for the standardized test statistic. Okay, so I need to know x bar mu s the square root of n. Okay, so my standardized test statistic all right, so it'll be t equals, I need x bar minus mu over s over the square root of n. So now what is my x bar? The x bar, remember, is 19,850. And do you remember how we found that? That was stated in the problem, right? Has a mean price of 19,850. So we wrote down X bar is 19,850. Also, S is 1084 and N is 14. Okay, so I've got my X bar. S is 1084. N is 14. And now what do they mean by this mu? Here's what they mean by the mu. The mu is determined by looking at your null and alternative hypotheses. My mu is, or the mu for the formula for standardized test statistic is going to be 20,500. So it's what's right here, this 2,500. So the mu here is 2,500. It should be actually like mu naught, the notation in the book. So it should match up with mu naught is what you would put in your calculator. And also sometimes in the book it's called, it's the K. Okay, so that's what we're working for. That's what we're working with. All right, so now we're ready to plug these in. We get 19,850 minus 2,500 over 1084 divided by square root of 14. Okay, we do 19,850 minus 2,500 divided by 1084 over square root of 14. So we should get negative 2.2436. So this is our standardized test statistic. Negative 2.2436. Now, using this picture here, remember our critical value, this is negative 1.771, right? And we just found out that our standardized test statistic is about negative 2.244. Okay? That's going to be over here somewhere, negative 2.244. Our standardized test statistic is in the rejection region. Okay? So our standardized test statistic, T equals negative 2.243613747, which is about negative 2.24. So it's time to make a decision. Remember, how do we make a decision? Decision is going to be, since we're using the critical value method, is the standardized test statistic in the rejection region? Yes. So reject H naught. So we're going to reject H naught. So we reject H naught. And now to interpret our decision, remember we need to have two pieces of information. Do we reject H naught or fail to reject H naught? And also, what is our claim? Is it the null or the alternative hypothesis? And so looking at this, our claim is the null hypothesis. So the claim is H naught. Right? Do you see that? The claim is the null hypothesis. So the claim is H naught, and we rejected H naught. So our decision is that, right? So the claim is H naught, and we rejected H naught. So our decision is there's enough evidence to reject the claim. So in conclusion, at the 5% significance level, there is enough evidence to reject claim that the average price of a 2-year-old sedan is $20,500. Okay, because that was our claim. So the used car dealer says, hey, look, on average, a 2-year-old sedan is going to be at least 20,500. Is at least. Can you see that? I know it's kind of small. But so the used car dealer is saying, hey, look, on average, 2-year-old sedan is at least $20,500. However, the sample that we collected of 14 had an average of 19,850, right? And so based on the sample that we took, it's too unusual, right? It's too unusual. So our sample mean is unusual compared to what the used car dealer is saying. So we have to say there's enough evidence based on the sample that we took. There's enough evidence to conclude that the claim is false, to reject the claim. Okay? All right, so now you might be thinking, man, Kalila, this took a long, long time. This took like 40 minutes. And the reason why it took so long is because I was going in excruciating detail, because I'm trying to show you how each little piece works. The second time we do this, we're going to do this now with the calculator, and I'm going to do it a lot faster, okay? And the more you practice it, the faster it'll go, okay? So keep in mind that the more you practice it, the more familiar these things will be, and it'll go a lot faster. Okay, let's look at this example here. An industrial company claims that the mean pH level of the water in a nearby river is 6.8. You randomly select 39 water samples and measure the pH of each. The sample mean and standard deviation are 6.7 and 0.35 respectively. Is there enough evidence to reject the company's claim at 5%? Assume the population is normally distributed. Okay, so I'm going to go through and I'm going to highlight the key phrases here, keywords. Okay, an industrial company claims that the mean pH level of water is 6.8. Okay, you randomly select 39 water samples. So it's randomly selected, so it's a random sample, and I've got N is equal to 39. And you measure the pH of each. So I'm going to have 39 different pHs. The sample mean and standard deviation are 6.7 and 0.35. So X bar is 6.7 and S is 0.35. Is there enough evidence to reject the company's claim at alpha equals 0.05? So alpha is 5%. And then assume the population is normally distributed. All right. So looking at here, verify you can perform the test. Sigma is unknown. Yes, we know that because we were only given S. Verify that the sample is random. Yes, that's written in the problem. And verify that the population is normally distributed or N is greater than or equal to 30. We were told to assume that the population is normally distributed. Okay, so now we are ready to go. And we need to determine our H0 and our HA. So we got to write down the claim using everyday English words. What is the claim? The claim is that the mean pH level is 6.8. That's our claim. Mean pH level is 6.8. Let me translate it into math. Mu equals 6.8. Let me write the complement. no one can even read that. That was a waste. Let me get a little neater here. Okay. So I need my complement. The complement, mu, is not equal to 6.8. Okay. Let's see here. Which one is my null and which one is my alternative? My null is going to be the one with the equal sign. Okay, so I'm going to have mu equals 6.8 as my null, and my alternative is mu is not equal to 6.8. My claim happens to be my null. Okay. Now determine alpha. This one is easy because alpha is stated in the problem. Alpha is supposed to be 5%. Alpha is 0.05. Now use t-test on your TI-85. So on my TI-85, I'm going to go to, or TI-84. So I'm going to go to t-test, which means go to stat, and then tests. So stat, go to tests, and then go to t-test. So for me, it's number 2, t-test. And it should have input, data, or stats. 45. We're going to choose stats for our input. Now, mu naught, x bar, sx. Let's see, I think we can make this big here. N. And then the next thing it wants to know the alternative hypothesis. So, not equal to mu naught, less than mu naught, greater than mu naught. And then calculate, and then draw. Okay, so where do we get the mu naught from? We get it from this right here, so it'll be 6.8. Okay, so our mu naught is 6.8. So we enter that into the calculator, 6.8. My x bar, that is my sample. That's my sample mean, that's 6.7.